take care of. So therefore, we're going to go ahead and go over the binomial and geometric. We'll do some notes on it, and then we will do some problems, because the best way for you to learn how to do this is by doing the problems. So if you take a look at the new packet that I handed you today, okay, let's go ahead and kind of do a little summary of some of the things we had talked about yesterday. All right, so here we go. First of all, the first thing that I want to talk about in this section, besides binomial and geometric, is sampling distributions. Okay, so it's really important that you understand population versus sampling distributions. So I'm going to go over that real quickly. So first of all, if you do not know the shape of the population, so let's say this is the population, which that wouldn't be because you can't have like a non-function. Okay, so let's say that that's the shape of the population, which, what does that mean is inside that shape? Individual pieces of data. Okay, so individual pieces of data are inside this shape. Okay, now it has a mean of mu and a standard deviation of the sigma. Okay, so that's the population values. Now, the central limit theorem says that if n is large enough, it doesn't matter the shape of the population, the sampling distribution's about normal. So down here, I'm going to draw the sampling distribution. And a sampling distribution is when you take samples of size whatever. Let's say I'm taking samples of size 50. Then I'm going to take 50 of these individuals randomly, and I'm going to average them and drop it down, and there's the average. I'm going to do that again. Take another sample of 50 and bring that average and put it down. So the sampling distribution, regardless of the shape of the population, will come out being approximately normal. Okay, now we also need to talk about, okay, well, what will the mean of the sampling distribution be? And what will the standard deviation of the sampling distribution be? Okay, so we already said up here, up top, the mean is this mu of the population with a standard deviation of sigma. So what does it look like from my picture that the center of my sampling distribution is? Same, good. So it looks like the center of my sampling distribution is the same as the population, mu. So that's all good to go. Now, what would you have to say about the variability of this sampling distribution down here compared to the population? What's it going to be? It becomes more compact. In fact, mathematically, it is the population standard deviation divided by the square root of n. Okay, so we've done this all before. And you have a sampling distribution because that would mean it came from somebody taking samples of size blank. All right? Okay, so there is kind of a summary, making sure you understand the concepts. Now, whenever I drop down samples, they are all of the same size. I cannot take, a sample of 10 and average that, and then a sample of 50 and then average that. They are all of the same size samples, okay? All right, and then additionally, let's see. I want to go ahead and let's take a look at some of the other notes. Now let's talk, that was sampling distribution stuff. Let's now come over here and talk about binomial and geometric. Okay, so I gave you some new notes that I think are kind of simplified from what we went through yesterday. And so I am on page 7. And so I want to talk right now about the concepts of the binomial versus the geometric, and then we'll do some problems that do all the computation of it. Okay, so first of all, here's ones that both geometric and binomial have in common. They both have either a success or a failure. Okay, you either stop at the green light or you don't stop at the green light. You either are wearing your seatbelt or you are not wearing your seatbelt, so it's a success or a failure. All right. Now, on binomial only, so this is different from geometric. You have a fixed number of observations and a set number of successes that you are looking for. For example, I might say, what's the probability that exactly 7 of the next 15 cars are wearing seatbelt? The driver is wearing their seatbelt, his or her seatbelt. Okay, so it's a set number of successes out of in a set number of observations. That's binomial. That differs from geometric. Do you know how that's different than geometric? What is the geometric of that kind of thing? I'm going to come over here to page 10. This is it right here. Down here, the very last thing on the bottom. It says on page 10, the variable of interest in the number of is the number of trials that you do until the first success. So that means how many successes are you going to get whenever you're doing a geometric? 1. Good. Once you have that success, you're done. That's how it's different than binomial. Binomial can have those successes sprinkled anywhere amongst those in set of items. So this is different because it's you obtain, you go until you get a first success. Otherwise, the conditions are the same. They are independent of each other. The probability of success is the same for everything. If you got a green light on Monday, that's not going to change the probability of you getting a green light on Tuesday. All right? Okay. Now, let me see here. I think that I can stay on that page. Oh, okay. Here we go. I'm going to go back to page 8. And I'm going to go to the middle of page 8 where it says calculating binomial. Now, I did already talk to you guys about this yesterday, but we'll just go ahead and take a look at this formula. So this one right here that I have starred is the formula. It is on your formula chart. It is how you compute the binomial probability. So in this case, it would be like out of 50 trials, what's the probability of getting exactly 7 items? Or out of 5 coin tosses, what's the probability that exactly 3 of them are heads? Okay? So here's this formula, which we did talk about yesterday. We have this portion right here is the combinations in successes, or in trials, K successes. Now, your calculator computes these combinations for you, but I have seen it show up as a multiple choice question on AP exam where they actually have this written out and you had to kind of recognize it. So in successes factorial, in factorial over the successes factorial times the failure factorial. Okay, so you got total factorial on top, and then it's split up, success factorial and failure factorial. For example, down here, when it says you want 5, or out of 5, you want to have 3 successes. Okay, so out of 5, you want to have 3 successes. Well, here's how you do those combinations. Out of 5 factorial, 3 successes factorial times 2 factorial is the failures. And that's the number of combinations, okay? All right, now, then this part right here I have highlighted in yellow is the successes. So that's P is the probability of success and K is how many you want. And then the pink portion is all about failures. The probability of failures and how many of those you want. Okay? All right. That's the main thing on that. The next page over, 2 pages over, takes you to this formulas right here in the middle of the page on how to get the expected value or the mean. So one thing I want you to tuck into your brain is that expected value and mean are the same thing. On average, what you expect to happen. Those are synonyms. So if you're reading a problem, you need to know that if they are asking you for the expected value, that's the same as the mean. And it gives you those 2 formulas. So it gives you, you can find from a binomial the mean and the standard deviation. Well, guess what? if you have the ability to get the mean and the standard deviation, then you have the ability to do the normal model. You can take that mean and you can take that standard deviation and you can get a z-score and then do that area with the normal model. Okay, so there's what's going on with that. Last thing on this, and then we're going to start some problems, I think, is for geometric, the expected formula is not on the formula chart. Okay, so this is something that you have to memorize. And basically the question would be something like this. How many, blanks, whatever it is, do you expect to look at to get the first success? So how many are you going to have to check to get that first success? And so that formula is that the expected is 1 over p. All right, and that is not on the formula chart, but you are expected to know that. So I should make a list of all the things that aren't on the formula chart that you kind of got to know the formulas for. Maybe I'll get that together for you guys. Okay, let me check and make sure that's all of the ones, and then we'll go do some problems. It is, so let's go back to the first page and work through some problems. We might have done some of these yesterday, so I'm going to go pretty quickly through these, and then we'll do some actual calculator stuff in a minute. All right. Number 1 says we have a binomial. We have n is 60 and the probability of success is 0.4. It wants to know the mean and the standard deviation. So how do we compute that? We use a formula. Perfect. Very good. So the formula is that n times p for the mean, and for the standard deviation, it's the square root of n times p times 1 minus p. This is on the right-hand side of the front of the formula chart. All right. So, of course, when we put those numbers in, it would be 60 times 0.4, which is 24, and then over here, it's the square root of 60, 0.4.6, and that ends up giving you 3.79. So that's A. We're going to skip number 2. We're going to go to number 3. Number 3 says you want to use the normal approximation for the binomial, for a binomial problem. Which of the following does not have to be true? So basically, it wants to know what are the conditions to be normal. Well, what are they, guys? What have I taught you? Get real. Come on, let's get real here. Random, independent, and large enough. Okay, good. So let's look at A. A says, and this is the one that we use, n times p is greater than or equal to 10. That's your successes. And n times 1 minus p is greater than or equal to 10. That's your failures for proportions. Is that one of our conditions for normality? Yes, it is. So that one's done. That's our large enough condition that we use. Okay? All right, how about this? The individual trials must be independent. Yep. Actually, independent, go down to answer choice D. The population size must be at least 10 times as large as the sample size. I'm going to translate for you. That one is saying n is less than 10% of the population. Okay? So, independent, n is less than 10% of the population. So, D is one of those ones that's needed. So, let's look at C. The sample size in the problem must be too large to permit doing the problems on the calculator. Is that one of our conditions for being normal? No. Okay, so that's the one that's not good. Moving on. We are going to do number 4. Okay, so here we go. Number 4. You form a distribution of means of all samples of size 9. Guys, it's key that you know that when you're doing a sampling distribution, they are samples of all the same size. Every single one in there is a size of whatever n is. Drawn from an infinite population that is skewed to the left. So there we have information that the population is skewed left. So here's the population. So we know the shape of the population. We know that it is not normal. So we're going to need some large enough stuff going on in order to fix the problem. All right. The population from which the samples are drawn has a mean, so the mean of the population is 50, and the standard deviation of the population is 12. Which of the following statements is true of this sampling distribution? So let's think about coming down here and doing a sampling distribution of samples of size what? 9. So I'm going to drop down and make an average of 9 items, another average of 9 items, another average of 9 items. So I've got a distribution down here of all these samples and the averages of size 9. So my question is, first of all, what is the mean of the sampling distribution? Good. It is the same as the population. So it's 50. How about the standard deviation of the sampling distribution? Is it going to still be 12? 12 divided by the square root of n, which is 9, so that's 4. All right, so I'm coming over here. Answer choice C and answer choice A are out of the question. Okay. All right, so now we're down to what is the shape of this sampling distribution. The question is, what is the shape of this sampling distribution? Your choices are skewed somewhat to the left, approximately normal, or the size is too small to make any statements. Okay, so in order to be approximately normal right here, do I meet my bases? Is the criteria for the central limit theorem been met? That's correct. N has to be greater than or equal to 30, and it is not. Therefore, it is not approximately normal. The sample size was not large enough to fix the problem. So D is out. So now we're down to it's either skewed left or sample size is too small to make any statements. The correct answer is B. And the reason it is B is because we know the shape of the population. Since they told us the population is skewed left, then when you take down samples, it's going to start fixing it. And if your sample sizes are big enough, it'll fix it completely and makes it approximately normal. But my sample sizes are not big enough. So it's going to be skewed left, just not quite as skewed. Okay, so it's going to be skewed, it's going to fix the problem some, but it's still going to have some kind of skew. All right? E would be the answer if we did not know the shape of the population. Okay? If they didn't tell us anything about the population, E would be the answer. But they told us that the population is skewed to the left, so therefore it is B. All right, does that make sense? Okay, number 5. Number 5 is going to be a notation and also we'll talk about how to do this in your calculator thing. So here we go. A 12-sided die has faces numbered 1 through 12. Assuming the die is fair, that is, each face is equally likely, which of the following would give the exact probability of getting at least 10 threes out of 50 rolls? So first of all, the probability of getting a 3 is 1/12, which is 0.083. So that's where all those 0.083s are coming from. Okay? Next, I want to talk to you about this little sequence I'm writing here. Okay? So this little sequence is telling me, 0 successes amongst the 50, or exactly 1 success sprinkled amongst the 50, or 2 successes, and so on, up to 50 successes amongst the 50. So what do I want if I want at least 10 successes? I want 10 to 50. Okay, so since I want 10 to 50, then I want to calculate that, but my calculator will not compute accumulation from a midpoint up. So how can I do that? Good. My calculator will accumulate a bottom portion for me. It will accumulate 0 through 9 for me, but that's what I don't want. So therefore, I'm going to do 1 minus the bottom 9. Okay? So let's take a look at our answer choices over here. This one says 1 to 9, that's not it. This one says 11 to 50. This one says 0 to 10, that one's not it. So it's C or D. What is the difference between C and D? One goes to 10 and one goes to 9. Which one do we want to take off? We want to take off the bottom 9 because I want 10 and up. So therefore my answer is D. C takes off too many. Now, calculator-wise, this would go into your calculator like this. 1 minus the binomial CDF of 50, comma, 0.083, comma, I am taking off up to and including what? What am I taking off? Up to including, that's 0.083. 9. I'm taking off the bottom 9. So that's binomials 1 minus binomial CDF of 50, comma, 0.083, comma, 9. That would be how I would do that in my calculator to get the number. Okay? 6, 7, I'm not going to do, and 8, I'm not going to do. I'm going to do 10, so let's talk about it. Sorry, number 9, I'm doing number 9. Okay, so on number 9, a school survey of students concerning which band to hire for the next school dance shows 70% want to hire the Greasy Slugs. What's the approximate probability that a random sample of 200 students has at least 150 will favor hiring the Greasy Slugs? So I want a sample of size 200. I want at least 150. All right, so talk to me about these representations. I see 2 of them are represented, the top 2 are represented binomially. Like a binomial, the bottom ones, C, D, and E, are represented like a what? A normal model. Yeah, because it's giving me a z-score. Okay? All right, so what do you think? What are these binomial ones having you compute? They are having you compute exactly 150. Am I wanting exactly 150? No. So they are gone. They're out of there. So obviously, I need a z-score. If I need a z-score, what do I need? I need the mean and the standard deviation. Okay, so if I put these numbers in there, that's 200 times 0.7, which is 140 for the mean. And then this one comes out to be the square root of 200.7.3. Okay, so let's go through this. What do you notice? Does D have a problem? Well, looking at E, what's wrong with E? You got to go X minus the mean over the standard deviation. What's wrong with E? Nope. They did the mean minus X. So they switched that, so that's a no-go. What's the difference between C and D? Okay. D has the wrong standard deviation because that's supposed to be the sample size of 200 there. So D is out. So the answer is C. All right. Now, I like some of these other problems, but I think before you get started on your assignment for today, which your homework is pages 31 to 40 in your packet, which is the next probability section. Okay? So that next section in your packet, before you do that, I want to actually go to page 6 and do problem 8 with you completely, because I'm going to just kind of throw some more wording out at you and see how you do. I'm telling you, with probability, the only way to get it is to practice it, so you just got to keep going on that. All right, here we go. Assume 13% of people are left-handed. We are going to select 5, so N is 5. Find the following probabilities. A, The first lefty is the fifth person. So what's that going to be like? Good. No, 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 yes. And of course those multiply together. Now, I would like to tell you that, is this a geometric or a binomial type of computation? You are going until you get a success. That's geometric. So if you were to use your calculator, which you wouldn't have to, you could just do the 0.87s times the 0.13. You would do geometric PDF because I want that success in a particular place. So geometric PDF, in order to put the first success in a particular place, and you do, what you put in here is the success and where you want that placed. So I want the 13% to occur in the fifth spot, and then that's how you could do that also in your calculator. Okay? All right, B. There are some lefties among the 5 people. What does it mean if there are some lefties? There's at least one lefty. And what do you know about at least one? Yep, 1 minus the probability that none of the 5 are lefties. I just set it on my desk. Okay? All right, C. I'm not going to do the computation, but that's how you do that. No, at least one. It can be one or more than one, right? Or more than one. There's some, yeah. I guess we're not going to do at least 2. We're going to just call that at least 1. All right. Next, the first lefty is the second or the third person. This gets lost with people. I get people wanting to just place the success in the second and the third spot. But there is actually 2 things here that we add together. We add the success in the second spot plus the success in the third spot. So it would take those 2 separate situations and combine them together. Okay? Yep, those are all like multiply, so correct. And then you go to how many you want, and then you stop. Okay? All right, next, there are exactly 3 lefties in the group of 5. What kind of problem is that? That is binomial. Those 3 lefties, and exactly 3 of them, are sprinkled anywhere amongst those 5 in any order. So that's got to be binomial. And so I want the probability that x is exactly 3. That is written as 5, choose 3. And then the success portion is first. And that is 0.13. And how many of those successes do I want? 3. And then 0.87. And how many failures do I want? 2. And here's how that will go in the calculator. Binomial, what? PDF, because in particular, I want exactly 3. Binomial PDF, and the numbers that go in there are NPK. So it is your number in your sample, comma, P is the probability of success, and then K is how many successes you want. I want exactly 3. So that's how you would do that computation in your calculator. All right, next. There are at least 3 lefties. Oh, so what does that mean if there are at least 3 lefties? So at least 3 I want, 3, 4, and 5. My calculator will not give me 3, 4, and 5. It will only allow me to take off 0, 1, and 2. Okay? So that will be 1 minus the binomial CDF, because it's the bottom, the accumulation of the bottom ones. Let's talk about what goes in here. The first number is 5, comma, 13, comma, up to and including what? 2. So I am taking off up to and including 2. So that's the way you would compute that. F, there are no more than 3 lefties. These ones mess with my head. So no more than, not more than 3. So what does that mean? Okay, so I want 0, 1, 2, 3. So how can my calculator do that for me? Do I need to do 1 minus? No, because I am accumulating from the bottom. So I just do straight up accumulation of binomial CDF of 5, comma, 0.13 up to and including 3. Okay, how many lefties do you expect amongst those 5? What did I tell you a synonym to how many you expect is? What is the mean? That is n times p. So what would that be here? 5 times 0.13. And I'm going to change question H. Question H is going to say, how many people do you expect to examine to find a lefty? Okay? How many people are you going to examine to get that first lefty? So how are you going to do that one? Why did that just do that? Yep. So that is the expected for geometric, which is 1 over p. And so that's 1 divided by 0.13. No, you do not, because this is on average how many you would expect to go. Yep. Okay? All right. So that's all that I'm going to have us go over with right now. Your homework is in your packet, and it starts on page 31. And I'm going to walk around so that I can make sure and answer your questions. Make sure you're on the right track, because these are tricky. So you have got to work on these. So start on the probability part 2, and that will be due on Monday.